I think we have quite a few people online and a few people in the open space as well. So thank you very much, everybody, for joining today. This is a bonus tech talk or an out of schedule tech talk. And I'm very happy to have today our OpenSI research team that is currently working on the CoSMIC project. And CoSMIC is a project that we are sponsoring as NetApp as part of our OpenSI collaboration agreement. And I have today Adnan and Danny and Carlos who are going to talk to us about CoSMIC. So over to you, Adnan.
Brilliant. Thank you so much for having me today. I'll start with the question that we're trying to answer, which is, wouldn't that be great if we had an automated system where we can ask our business processes in plain English, and that will spit out Cadence workflow code with error handling and fault tolerance, all of the plethora of things straight away. That's what we're trying to achieve here. And we will show our progress, what we have done so far today. So I am a PhD candidate at the University of Canberra. I've just completed my first semester. And I'm excited to present my research, which is cognitive AI for automated development, where we are focusing on redefining intelligence in workflow automation. Okay, so my research has been made possible with OpenSI PhD scholarship and National Industry PhD program under the supervision of my supervisory panel comprised of Dr. Carlos Cohen, Dr. Ibrahim Radwan, and industry supervisor Emmanuel Wintercrest, who's
that's me.
Whose expertise had been monumental for this research. Now, during my master's, I came across this lecture from Stanford online. It was taken by Dr. Andrew Yan, where he mentioned AI feels like a magic when we don't understand it, which resonated deeply with me because during that time I was working with machine learning models, and we had tools like SHAP Online, where we can perform sensitivity analysis to say that which feature contributed most to a prediction for AI. Right, but now we have generative AI, which can hold a conversation like a human. It can solve reasoning tasks. It can write code. But with those tools, SHAP and Live doesn't come into play anymore because a sensitivity analysis doesn't really help to understand why a generative AI model would predict such thing, mostly because it has a vast parameter space and a very complex attention mechanism. So to solve that, to get out of this black box issue, that's our research goal. We would like to measure cognition of AI systems in a systematic way, and also we would like to present ways that we can enhance those cognition qualities so that we can enhance the overall performance. Before I do that, I'll probably start with the definition of cognition that we are advising, which is we define cognition as an AI system's ability to process, integrate, and apply knowledge to a specific domain. The domain can be chess, which we used as a proof of concept. It can be code generation, anything. And all of those cognition, we define those as the 5 major qualities, which are anticipation, attention, memory, perception, and reasoning. So our hypothesis is if we can provide specialized supporting services that target specific cognitive qualities, we can measure and improve performance in domain-specific tasks. Now, this hypothesis has 2 components. The first component is, can we actually measure those cognitive qualities independently? And can we target those cognitive qualities and enhance those? So our first major breakthrough came with a cognitive system of machine intelligent computing, or what we know as CoSMIC. For this proof of concept, we used chess as our testing ground. And why chess to start with, which is chess is a deterministic environment. On top of it, we can simulate hundreds, if not thousands of games without any computational overhead. And at the same time, we will need all the cognitive qualities that we mentioned to work in harmony so that we can get better in this system. Now, at the core, we have our LLM agent. So that's nothing new. But this LLM agent is usually supported by other services. For example, for this proof of concept, we had the chess engine service, which essentially is Stockfish 16. At the same time, we have the vector database update and vector database service that can aid the LLM agent. For example, if a user asks a question like, what would be the best move given this is the board state in FEN, let's say, then the query analyzer will not, which we'll get into in a minute, will forward the traffic not directly to LLM agent. It will forward the traffic to the chess engine so that chess engine can provide some comprehensive analysis on what would be the best move and then pass that suggestion to LLM agent. At the same time, vector database can provide a concrete example of what was the past pattern of games, provided that this is the board state. And then LLM agent can combine all of those information and synthesize an output that is meaningful to the user. So that is the main idea. Now, the entry point for CoSMIC is the query analyzer service, which essentially is like a traffic controller, which routes the user query to the most appropriate system. For our proof of concept, as I mentioned, we had chess engine, vector database, and to support the vector database, we have vector database update service. Now, with us, we had remarkable results, which we'll get into in a minute, but that proof of concept showed us that not only we could measure cognitive abilities in AI systems, but actively we can enhance them through carefully designed supporting services. Now, the system performance, we did some comprehensive analysis with 4 language models, which are GPT-4, Mistral 7B Instruct, Gemma 7B Instruct, and then a fine-tuned version of the Mistral 7B that we used earlier. Now, for this, we just didn't rely on overall performance metrics. We broke down the performance among the 5 qualities that we mentioned. And with the blue lines, you can see that ChatGPT-4 performed quite well across all of the cognition qualities with some variations, for example, perception in reasoning. From that, we can see that the open source models, which is Gemma and Mistral, it did fairly well. It wasn't very good. So we jumped into the second phase of our experiment, which is how can we enhance those qualities? So we have the measurement done. How can I enhance that? So we took the Mistral 7B Instruct model back again, and we curated 2 datasets, which were reasoning and perception. The reasoning dataset was comprised of synthetic data we got directly from ChatGPT. So we asked questions and tried to mimic the reasoning capability of ChatGPT, provided that ChatGPT-4 actually had the best result. So we want to see that if we can mimic that result with the 7B parameter model. And for perception, we curated a few modules ourselves, and we created a perception dataset. And then we fed all of those, the perception and reasoning dataset, and see what is the effect. So after fine-tuning, the most striking thing that we saw was we had a positive spillover effect, which means we didn't just gain on perception or reasoning. It positively impacted memory and attention as well, marginally, but still it did, because our target quality was perception and reasoning. So that's the best thing. Moving on from that, one more major breakthrough was we get, with the perception, you can see that we can comparable result with ChatGPT-4, and in subsections of that perception dataset, it actually beat ChatGPT-4, and that's, we can see that we can achieve comparable, if sometimes even not better results with a much smaller model, because ChatGPT-4 is supposed to have more than 1 trillion parameters, and we are working with the 7 parameter model. So from this, we can see that success was not just numbers. It validated our approach that, like, with targeted fine-tuning, with targeted additional services, we can enhance the performance of a model. And raw model size always isn't the only path. Thoughtful enhancement of specific cognitive capabilities can yield comparable results with far greater efficiency. Now that led us to our first publication, which we presented at Australasian Conference on Information Systems, where we presented our framework for decision-making interpretability and domain-specific expertise and integration. Now, before I move on to Cadence and what we have been doing in the last couple of months, I want to talk about MOE, Mixture of Experts, one of the hottest topics at the moment, which surprisingly aligns very well with our CoSMIC architecture, which actually is an incidental, even though MOE is sort of a recent improvement. So recent development in AI today. So fundamentally, MOE has a query router, which acts again as a traffic controller, and it will route user query to the expert network. And in our case, we are routing query to the expert services. That is the main difference. Other than that, it sort of follows the exact same architecture. And the fundamental principle, when it validates, we can see that MOE powers models like DeepSeek and Mixtral, which achieves usually state-of-the-art performance at the moment. That was right before GPT-4 and GPT-4o1 hard models. So that sort of validates our approach that instead of just relying on huge parameter models, we can combine all of these specialized services to get better performance. And it also validates our approach in another angle, which is just because we have all the services for every query, we don't need to activate all the service. We can just target one service and then activate that. So that was the striking resemblance that we have with MOE. Now, the first part of our hypothesis was how do we measure cognition, and we defined cognition. Now we divided those cognition into 3 layers, which is the task layer, you've got the quality layer, and the sensing layer. The task layer, I will probably give it with an example. Think of an e-commerce website. So you've got the orders coming in, you need to process payment, you need to check inventory, you need to organize shipping, and then you have to combine all of those microservices so that they can work in harmony. So those subtasks, we can think of that they stay in the task layer. So for example, let's say that processing payment, that's one of the tasks. And now we go into the quality layers, which is very intricately connected and they interdepend with each other. That's what we are actually trying to understand now, how we can access this interdependability. But the 5 qualities that we mentioned, for example, perception for that task, it will probably look at the service health. So how is the payment processing service that we have? How does it look like? Do I have good connection? So that's perception. Memory is it will look into other payment details, like which route did it follow? So the history part, my knowledge base. Reasoning, that will take the ultimate decision. Attention would be following the subtask of that task. So for example, for processing, like processing payment, that will go to certain API, make the call, transfer the balance. So that where attention focuses on that particular subtask. And lastly, we've got anticipation so that it will predict a point of failure in case that happens. So we can see that by mapping these relationships, we can measure exactly how well an AI system understands any domain. In our case, that was the Cadence workflow domain. And this is sort of like we can think of a cognition MRI. So we know exactly how it's thinking, not just getting the result. Now, we'll jump into our ultimate goal, which is Cadence. Now, I'll try to explain what Cadence is with my limited knowledge to a room full of Cadence experts. So I'm not trying to teach a fish how to swim, but I like you to just humor me for a moment. So basically, Cadence, from my knowledge, is a stateful fault-tolerant workflow engine that handles one of the most challenging aspects of distributed system, which is managing scalability, reliability, and availability of business processes. And we can go back to our e-commerce example again. So we have the orders coming in, and then all of those processes, the payment, the inventory, looking up inventory, then thinking of shipping, and then managing all of these microservices in harmony. All of this has to happen in a sequence. And if one of them fails, what Cadence does is it lets you start from that exact same state. So it is stateful. It keeps that state and it lets you restart that process again. So that's what we are trying to achieve. Like we would like to input as the business requirements and business processes and output the Cadence workflow code. Now, a traditional machine learning model can help us with that, which is like it will just follow the happy path. What about the trend, whatever they're doing, we'll just follow that. But that doesn't guarantee that the machine learning model would understand the business workflow. So we need a reasoning model that can actually reason through each and every task and say that, okay, this one has to happen before that. What state do I need to hold on, etc., etc. So that's what we are trying to achieve with our CoSMIC project. Now, we already have looked into our first hypothesis, the first component, which was how do we measure it? Second part is how do we enhance those qualities? For those, we have another proof of concept that we just finished. That was it's under peer review at the moment. We started with another test ground, which is this time is code generation. Our ultimate goal is code Cadence, but this time we want to start with something a bit more concrete, where we can have the benchmark datasets ready so we can test our approach. That's the idea. So that's why we went with Python code generation, and the benchmark datasets that we used to evaluate our code generation was HumanEval, MBPP, which is mostly basic Python programming, and Big Code Bench, and the extended version of HumanEval and MBPP, which has extended test cases and extended description. Now, HumanEval has 164 human annotated problem statements, along with MBPP has 974, and Big Code Bench has 1040 problem statements, and they come with test cases and usually function signature. Now, meet PyCapsule. That was our most recent work. Now, before I get into PyCapsule, I would probably mention that this works on an agentic feature, which is one of the hypes at the moment as well, right? So everyone wants to implement agents, get the work done. But one of the one of the drawbacks of agentic architecture is it doesn't tell you that the agent number doesn't usually correlate with effectiveness. For example, if you have 500,000 agents working for one problem, probably all of these agents can bring in something on the table to solve that problem, but that raises another problem, which is you will have computational overhead and heavy token usage. So, and now those outputs, they're not usually deterministic. So you actually don't know where they're going. So what we went with is we still have the agentic architecture that is so famous at the moment, but we use minimal 2 agents. And the 2 agents that we have, one is the programmer agent, which is a smart agent. So it is powered by a generative AI model, LLM. We used GPT-4, GPT 3.5, and an open source model called Qwen 2.5 Coder from Alibaba. And then we have got our executor agent, which is basically just a Docker container, so it can take the generated code from our programmer agent and executes that. Now, we use Docker container mostly because we found out the hard way that it is quite adventurous to let an AI agent like execute code on your local machine. It freezes, it does heaps of things. So I'm getting code and my reasoning from my programmer agent, generated code. We are taking that code and executing it in our executor agent. 2 agents. But to support those agents, we have these automated pipelines, which we call them modules, which are function signature converter module, and you've got example detection module and error handler module. Now, what are these? The function signature converter module, that comes in play only for MBPP. So what the datasets that we talked about, all of them has problem description and a function signature saying that there's the function signature that you need to follow, except for MBPP. And because of that, the code generation is very unstable. Now, this had been reported by other techniques like Agent Coder and in the technical report of Qwen 2.5 Coder. Now, to solve that, they proposed a 3-shot prompting technique, but to make everything comparable, because we would like to compare MBPP with HumanEval with Big Code Bench, right? So we cannot just implement 3-shot example for MBPP and the rest of them. We're using the dataset provided function signature. So what we did was we used this signature converter module, which takes the problem description and use one of the test cases and creates a function signature that we can compare with other datasets. Next up, we have the error handler module. That what it does is it takes the error messages and process that error message, very much like a software developer would do. So it will take the whole error message, first figure out what the error type is. Based on the error type, it will probably give you some direction. For example, for for a test case failure, you will have this is the test case that you failed, and probably just to provide you a bit of context. That's what it will help. At the same time, for example, we had recursion errors. So we had actually a recursion error that exceeded the context length. So I think it went up to 1 million something lines of error messages. So when we pass that to our LLM model, it just broke straight away because it exceeded the context length. So that's what it does. It takes the error message, check what type it is, and provides you some context. That way it can guide the LLM in a better way. Lastly, before I get into the example detection module, I will say we also have a time-safe thread. Basically, that every code that the programmer agent generates, we execute that code in a time-safe thread mechanism. Basically, we would like to monitor how long does it take to execute a code. If it exceeds a certain threshold, for let's say 100 seconds, we will raise infinite loop error because that happened quite a few times. Now, when we execute the code in that time-safe mechanism, which is all good, we can all account to that. But the problem is sometimes my programmer agent will do example calls in its code. So that's where example detection module comes in. It comes in and removes those example calls so that my code is safe to execute. Now, and lastly, our programmer agent had five debugging attempts. So your zero-shot first approach, and then on top of it, you get 5 extra attempts. Now, this is the results that we have so far, and we managed to achieve state-of-the-art performance for human-able ET, and Big Code Bench, where we almost got 20% more accuracy. Now, the models that we use, you can see that we had GPT-4, GPT-3.5, and the open source model Qwen 2.5. All of them, they seem quite nice, except look at the last 2 rows, which shows you what happens when you integrate PyCapsule with the base LLM and what happens without the PyCapsule. The other approaches, there are other debugging-based approaches that we found that the previous works. We managed to get, as I mentioned, state-of-the-art performance in that section. But at the same time, the last 2 rows that shows you the effect of PyCapsule when you integrate it with a base LLM. With Qwen 2.5, of course, we had massive improvement, but we actually managed to achieve Qwen. We actually managed to outperform Qwen 32 billion parameters performance with our 7 billion parameter model. So which was the major breakthrough that we had just by integrating PyCapsule. So that tells you how effective we can be with PyCapsule and our automated pipelines. Now, we'll look at the success distribution. That's coming from Qwen 2.5 7B instruct on all the benchmark datasets that we used. And you can see that the blue portion, that shows you the zero-shot attempt, and then you've got your first debugging attempt up to 5. We can see straight away that usually on your very first attempt, which is the zero-shot attempt, you'd be able to solve most of it, which is no surprise. And then as my debugging attempt increases, the sort of success distribution, it starts to diminish a bit. Which, I mean, I don't think it's a news for anyone. Like, we can see that probably because the complexity is rising, so that, like, of course, the success distribution will go down. That's no news. But then we did a bit more test on that. The graph on the right, it shows you exactly what we showed in the pie chart, which is like, you're getting diminishing effectiveness. But then what we did was we normalized the effectiveness again. The way we did it is, let's say that you've got 1,000 problems and only 500 of them reached attempt 3. And then in attempt 3, if you manage to solve 100, then we will say that on third attempt, your success distribution was 20%, right? So that's just the normalized bit. And then still, when we plot that, we still see that trend, which is even when you normalize that, the success distribution, like the trend is still the same, which sort of starts to make sense. I'm still like, okay, well, because those are harder problems, probably that still makes sense, right? But then we did 3 separate experiments again, where we took only the problems that it could not solve. So only the harder problems, right? We ran those tests, exact same result again. So that's what sort of tells you probably there's a natural debugging window, a debugging span that probably exists that we don't know about just yet, where like after probably 3 or 5 attempts, it's just better to start from the beginning or probably try new techniques. That's something that we will have to, that we will look into soon. But yeah, that was one of the findings that we had on our very recent work. And now we have started working on something that will actually contribute directly to the Cadence workflow, which is what we have noticed with LLMs is once I give it a very good direction, which is this is your function input, this is what I'm expecting, this is what I want to do with that function. It usually can do pretty good job, but it is that direction. So for that, we again went back to our agentic framework, which is we will bring in quite a few agents. At the moment, we are testing with 4 agents, and we want to see that how those agents can bring in what they can bring into the table and how it can provide some solution for a given business problem. So that's what actually we are trying to get to with the business requirements that we usually would get a customer if we get an example for that. So the agents can work on those on that problem and say that, okay, to solve this issue, you'll have to approach that problem with these and these steps. So yeah, so that's what we are working on at the moment, along with the other one that we showed where we are just analyzing the trend. That concludes my presentation, and thanks so much for listening. If you have any question, I'd love to take it now.
Thank you.
Thank you.
I feel it's mother.
But it take more than 20 minutes.
Did I? Okay.
That's all
I
right.
got carried away.
Yeah.
Do you have any plans to rerun any of these experiments as more models become available, especially with like reasoning models?
Yes.
And do you have any way of sort of going, oh, does their definition of reasoning match up with ours and that sort of thing?
The reasoning, unless the reasoning architecture change,
Yeah.
like with the neural, we don't have the current implementation. All you have to do is you have to change the name of the model. That's
Yeah.
it. It can adapt to any model straight away.
So you're showing results for the ones who actually already perform best.
Yeah.
Yeah.
Or the other models, like you get the ones who you're knowing is best for doing the code generation in Python. For example, we did a very fast check with like a DeepSeek.
Yeah.
For example, did not perform
Yes,
as well
well. It talks a lot.
because it talks too much. You got lost.
It just does not stop.
Interesting.
Yeah, because we had the DeepSeek. Even we ran our first experiment with I think Llama 3.2, which is we are focusing on the instruct models mostly because you sort of can guide them. For example, I think I mentioned that even though so our programmer agent sometimes it adds example calls, right? We mentioned that, but in our prompt we explicitly say that do not do that, but it doesn't usually listen. But it's like instruct models are quite decent when it comes to stuff like this.
Yeah.
But the other models, for example, DeepSeek, it doesn't have an instruct version.
Yeah.
So I think that's why it just talks too much.
Yeah.
For the debugging, it's like you're saying, that it's up to the 5th. And it's just completely diminishing returns, continuing, right?
Yeah, from 4th attempt actually.
Yeah, from the 4th, sorry.
Yeah.
Have you been able to see a pattern in what it's doing at the 6th and 7th and whatever? Like, is it
Yes,
is it just completely going off the rails?
No,
or
no,
is it-
6th or 7th, it goes, I think, 0. The third experiment that we did, that was, I think, 0.0 something. It wasn't like a single digit, it was 0.0 something. That's what I remember from the last experiment, the effectiveness. So that's why we said that probably like there's a natural window span after that, because the confusing thing was after 5 attempts, we still have some problems that it couldn't solve, right? And then we go back and give the same problem again with a fresh start. And then it managed to solve 3 of those, and then even there, you see the same trend again, which is like in a diminishing trend after 4.
And the question is, what we hypothesis is when you start a problem from fresh, and then the implementation not going to be always the same, but then there is a bug, and then go for what the agent does, and then he tried to solve that bug. When they solve that bug, he creates much more bugs than originally he has.
Yeah.
And then that's why then we said the complexity starts to become bigger to fix. And then that's why if you go back then to the start point and now try again, start 0 without listening to your new upgrade code. That's what you know. It's like when the solution could be simpler because he is starting just to patch the old thing. He started with like a logic not so perfect, and then starting solving the problem with a much more complex way to solve the problem, what then generate much more challenge to debug. And that's why you will notice, like, if you give more than 5, it's still you're gonna get in that the loop of not being able to fix all the issues later.
Thanks. It's a really good explanation. It just it sounds very human-like.
Yes,
Yeah,
exactly. It's very human-like. That's what the framework of the cognition is based in human psychology. We have we are applying that same framework for robots. We collaboration with the team of robotics at UC, where then we have a team of psychologists as well in the cognition space to see how would you treat that as a human, and then we can see if we start treating AI like humans, if they work as a human. That's why you're framing like that as well.
Does anyone online have any questions?
All good, no, I think.
Oh, Paul posted something.
Well, he asked if you can ask.
Yeah, please do ask remote questions.
In the chat.
I know, I see it here.
Yeah.
I have the view here.
Oh yes, I am. Hello. Hi.
Hi,
Cool
Paul.
talk. Thank you. I'm sorry, I'm Paul. I haven't got my camera at the moment. I'm the Instacluster tech evangelist, and I have used Cadence. So I'm just curious. One of the main value propositions for Cadence is that it's a code as a workflow engine. So is one of your main goals to essentially remove that aspect to make it a lot more user-friendly for people that aren't programmers?
Like our AI system to adapt to that, just to understand it first, the business problem, and then adapt to it. Let's not follow a simple trend. So yeah.
So then, I guess another question is about debugging. So at that point, I mean, one of the main activities that I've spent with Cadence is that trying to actually debug the code. But if you're essentially removing the end user from the code, so your modeling approach and the machine learning approach would essentially have to do all the debugging itself. Is that
Yes,
correct?
yes. So we have the feedback mechanism. So that's where our error handler
Yep.
module comes in. So it
Sure.
makes the error message a bit more user friendly so that it can guide the generative AI model.
Right. So that's not, you wouldn't really even be presenting the errors to the user at that point. They wouldn't
No.
even see the
No,
error message.
it logs it. It logs it, and then at the end, if it can't solve it in 5 attempts, then we return all the error messages and whatever happened, the whole history.
Okay, interesting.
It's a support for the developer. Like if you have the developing, you're going to be able to code much faster because you're going to reduce the number of debugs. You're going to just treat only the debugs that the system actually could not. But
that's
if
sort
you
of not a
reach the
zero
number,
code approach at that point. It's sort of like a code assistant, maybe. Yeah,
code assistant. Yeah.
Have you no, sorry, another throwaway idea is, have you thought about using any sort of chaos testing to see whether more complex types of errors can be handled? Like, I mean, I know Cadence works really well with the replay mechanism and stuff, but I mean, have you tried thinking about introducing different types of failures, delays in other systems, etc.?
Just not yet, because we're just focusing on Python for the time being, because we don't have any other benchmark data set to test or integrate any other failure.
There's probably some sort of chaos framework for Python, is there? I assume. I don't know.
Yeah, we just not look at that. That's very good check. We're going to have a look on it.
Anyway, just an idea. I know a lot of people are using that type of tool increasingly on things like Kafka for the new KRaft protocol. They're actually essentially running simulation testing and chaos testing on it to see whether it is correct or not. So, yeah.
Something that we can look into. Yeah, absolutely.
Cool. Any other questions in the room or online? I hear only silent rapture. Thank you very much. Thank you, team, for coming today. And thank you very much, everybody, for attending.
Yeah.
Being out of a job.
No, that's why I say is